Hi everybody, welcome back. Again, we're still going on to chapter 11, and the last section we were talking about sequences, and today what we're going to do in this video is we're going to visit what are known as series. So on here on the screen, what you'll see is that I have two sides set up. One side denotes the sequences, and the other side denotes the series. Now, sequences and series are typically broken up into two different portions. One is going to be a finite, either sequence or series, and the other one's going to be an infinite sequence or series. Now, if you look on screen here, I gave you a quick example as to what an infinite series might look like. Infinite sequence might look like. That sequence is just a list of numbers that we are collecting together to make that sequence. However, if we wanted to turn that sequence into a series, all we then have to do is add all the individual terms in that sequence. That is the difference between sequences and series. Alright, now, whether it's infinite, we just keep adding the rest of the terms forever. Same thing for series. Series, we're just going to keep adding them instead of listing the terms for infinity. Finite just means that we have a stopping point somewhere. Doesn't need to necessarily be 4 terms. It could have been 5 terms, 6 terms, 7 terms, 8 terms, 9 terms, 10 terms, 20, 100, whatever many terms we would have some stopping point. That is what makes a list or a sequence finite. If we wanted to interpret it as a series, all we would have to do then is add all those individual terms. Now, the notation. The notation, as we discussed in the previous section, infinite notation looks like this, finite notation looks like this. Again, infinite, we go all the way to infinity, or we approach infinity, and finite, meaning that we stop at some value. Typically, I denote it as capital N. Now, I want you to pay attention to this series notation. That series notation is very, very similar. The only difference is that we use sigma to denote that we are converting that sequence into that series. I want you to then also notice the functions that we use, or this notation that we use. It's the exact same notation. We take this explicit function that is given by this sequence, and that is the explicit function that we use to develop this series. Alright, so if we have an infinite series, that's going to be awesome, but say that we only want to take a small portion of that infinite series. That means that we're only taking a finite sum of that series. In other words, we are looking at a partial sum. Now, anytime that we stop at some value that we're going to be adding, in other words, anytime that we're looking at a finite series, that means that we're really talking about some partial sum of some infinite series. Now, this whole idea and this whole concept of a partial sum is going to be very beneficial to us, because as we start looking at some of these sequences or at some of these series, and we want to identify, are they convergent or are they divergent? Well, if we analyze the partial sum, that actually gives us an insight as to whether the series is going to be divergent. All right, so if it's not divergent, then we can rule that out and everything will be just fine. All right, so this is what we want to look at when we're looking at sequences and series. The notation is going to be key, as well as the terminology. So, one of the very specific types of series that we have is what's known as a geometric series. This geometric series has a few items that we like to look at. All right, number one, we want to look at what is the initial value that we start that list at. All right, so we want to extract what is the very first term that we're going to be adding. In other words, what is that A value? Number two, if it's a geometric series, that means this has a geometric sequence associated to it, which means we have a common ratio. So R is your common ratio. Notice that if we take this infinite series and if we find the sum for this infinite series, meaning it can converge, we will have this sum that arises, or this formula that we will be working with. Notice, we're going to be looking at the common ratio. Is the common ratio less than 1? If it is, then the geometric sum converges, and we can find what it converges to. Number 2, if that common ratio is greater than or equal to 1, then the geometric series is going to be divergent. All right, so we have a few things that we need to worry about, a few things at our disposal that we're going to want to extract. All right, so with that, let's go through and let's finally start looking at some examples to help us tie in this whole process of series. All right, so here's your question that says, we want to determine if the series is convergent or divergent. If it is convergent, find its sum. So what I'm going to do here is I'm going to use a few properties that we kind of learned back in algebra. And that property is that if I have a constant that is multiplying my function inside of my summation, then it can factor out. Oops. So what I have here is this function. Now what I'm going to do is I'm going to rewrite this slightly different. I'm going to rewrite this as such, 1 over pi, and this is going to be to the power of n. All right, now what I'm going to do is, typically I would like to stop here. However, I want to show you a little bit more. What would happen if we expand at this point in time? Well, if we expand, then that means we're going to have 5, and that 5 is going to multiply the first term where n is equal to 1, which is just going to be 1 over pi, plus the second term, which is n is equal to 2, which is going to be 1 over pi squared. And then we can keep on generating this series. Plus, and we could keep going. Now, within this whole process, what I want to do is I want to extract from here. Let's go ahead and let's start extracting. What is the a value and what is the r value? So I need a common ratio. The common ratio here is just this 1 over pi. As such. There we are. Now, what is this a value that we're going to be looking at? Well, the a value is going to be this very first term that we then start identifying. Well, if we multiply this in, that very first term is just going to be 5 over pi. So notice, did I really need to go through and expand this whole process in order for me to identify what is the common ratio and what is the very first term? The answer is no, we didn't need to do that. The only thing that we do need to see from here is that since we have the common ratio as 1 over pi, the absolute value of that is less than 1. If this is the case, then that's going to tell me that when I find this partial sum, it's going to be a, which was this 5 over pi, divided by 1 minus r, and 1 minus r, that's just 1 over pi. So as we then get to see, well, what is the answer to this? Well, let's see. We're going to have, let's multiply by pi on both sides, top and bottom. So this will leave us with 5 divided by pi minus 1. And there it is. So, is it convergent? Well, we could have said from here, the series is convergent. And why is it convergent? Well, it's convergent because the common ratio is less than 1, which means, hey, we have a convergent series and we found its sum, which in our case, that's really awesome. So that's awesome. That's number 1. All right. So let's go on to a second example then. Let's go on to part B and see if we can extract everything for part B as we did here. So for part B, let's look at this sum. This is going to be n is equal to 1 all the way to infinity, and this is going to be 1 divided by 3 to the power of n minus 1. Notice there's nothing that I can really factor here, so I'm going to keep this as is. All right. The only thing that I am going to do is I'm going to rewrite this differently. N is equal to 1 here, and I'm going to rewrite this as 1 divided by 3 raised to the power of n minus 1. Now again, if you want to go through and list all of these values, by all means go through and list them. All right, I'm going to show it in green so that you can see what is the listing of those values. So in here, let's see, if n is equal to 1, then we get 1/3 to the power of 0, which is just 1, plus n is equal to 2, so that's just going to be 1/3, plus the next value, which will be 1/9, and we keep going on forever. All right, so what I'm doing here is I'm just going to extract what is my a value and what is my r value. Common ratio, 1/3. A value, well, since this is in the standard notation that we were given, the first one is the very first term is going to be just 1. So at this point in time, what I'm looking at is the absolute value of 1/3 is less than 1. This tells me that the series is convergent. So if it's convergent, then that means I must be able to find its sum. Well, according to the formulas that we have, it's just going to be a divided by 1 minus r, which in this case is going to be 3. So at the end of the day, we get multiply both numerator and denominator by 3. So this is going to be 3 divided by 3 minus 1, my apologies, which is then just 3/2. So in other words, this series does converge, and that convergent number is going to be 3/2. Awesome. Now, if at any point in time this common ratio, or the absolute value of that common ratio, if it was not less than 1, then we would stop right there and we would say the series diverges. All right, because again, the common ratio would be equal or greater than to 1. Awesome. So let's go through a few theorems. That way we can get those theorems and we can further test whether a series is going to be convergent or divergent. All right, so I'm going to put the theorems on screen in a little bit, so bear with me. All right, so here's your first theorem. This theorem says that if you have a series, the summation of a sub n, as n begins at 1 and it goes towards infinity, if that series is convergent, then what this is going to tell us is that the limit of that function as n goes towards infinity must be 0. All right, so that's going to be interesting. All right, that's definitely going to be interesting. And one of the items that we could then see is we could use one of these arguments that we saw either in part A or in part B. All right, so let's look at this argument here in part B. All right, so it says that if the series is convergent. Okay, so I have this series. We were able to determine that it is convergent. So because it's convergent, I'm then going to start looking at the limit of that function to see if it is 0. All right, so let's see if that limit then, as n goes to infinity for this sequence, or for this explicit formula, 1/3 to the power of n minus 1. Well, if we go through this whole process, this is going to be the limit as n goes to infinity for 1/3 to the power of n minus 1. Notice as your n gets very large, this denominator is just going to get very large and large and large, which means the overall fraction is going to tend to 0. And that's exactly what this says here. That if you want to look at the series and you find that the series is convergent, well then the limit automatically for that function becomes equal to 0 as n goes towards infinity. Now we have to be very careful. the converse of this statement is not true. All right. Now, there is one specific function that you might find that the series diverges, even though it has a limit of being equal to 0 for that function itself. All right. So we have to be very, very careful with that the converse is not true. All right. But then again, how do we start testing for this? So give me a few seconds and I will prep you with what kind of test we're going to need in order to clarify this just a little bit more. Alright, so here's going to be what we're going to be using. We're going to be using this test for divergence. Alright, the test for divergence says that if we can find that the limit of my explicit function for my sequence as n goes to infinity does not exist, or if the limit is not equal to 0, then we have that the series that uses that formula and tends to infinity is divergent. All right, so this is a test for divergence. If we cannot find that it converges, it might be divergent, and let's go through and let's find that. All right, so we have to be careful when we're looking at series, because some series can be deceitful, and we have to then be very, very observant. All right, so the one example that I want to show you here for this specific theorem as to why the converse is not true, well, I want you to then take a look at this. What is the limit? And actually, I'll do this in a different color because I want to save that red for something else. Take the limit as n goes towards infinity for 1 over n. If you take this limit as n goes towards infinity for 1 over n, all you're going to get is 0. However, if you then take its sequence, take its series, start its series at n is equal to 1 and do this for 1 over n and send it off to infinity, this sequence diverges. It's kind of counterintuitive, right? Because you're thinking, okay, well, these fractions, 1 over n, the first one's going to be 1, then the next one's going to be a half, then 1/3, then 1/4, then 1/5, so on and so forth. Naturally, we should be thinking that this makes sense, that we should be able to converge. However, it's counterintuitive in the sense that it does not converge. This one actually diverges. Even though we find a limit for that function to be equal to 0, the function itself, if we take it as a series, does not converge, which means, again, the converse is not true. So we typically call this the harmonic series. The harmonic series is this series that we look at. And this is actually going to be very, very beneficial for us throughout the rest of the semester, throughout the rest of this course, because if we stumble across the harmonic series, we automatically know it's going to diverge. And if it diverges, we can use that as a comparison to determine whether other sequences or other series actually diverge or not. All right. But once again, we have this test for divergence and we want to use it. So let's go through a few examples to see if we can then identify any one of these items or any one of these series to converge or diverge, and see how we're going to be implementing these different techniques that we are just observing. All right. All right, so let's start using this. Now, here's an example that says determine whether the series is convergent or divergent. If it is convergent, find its sum. So the first example that we have here is where we have this infinite series and we have the function given to us as 2 divided by n squared minus n. All right, so some of you might be saying, hey, Mr. Castro, well, can we factor the denominator? Can we do different instances? Yeah, sure, we can do all of that. All right, so you can definitely try it. Now, the part that we're at a disadvantage at is that I'm at home recording this video and you're going to be at home watching this, where you're not going to have those different types of opportunities to present to the whole class. However, you know, it's always very nice for you to attempt it on your own. See what kind of discoveries you guys make. Take those paths that you're thinking of and see if that thought process will lead you down a correct path. All right. So what I'm going to do here is I'm going to start looking at this series. All right. That's nothing too bad. Now, my first instinct here might be to just go through might be just to go through and to find out what is this sum. So I'm going to substitute in a 1 in here. So 2 divided by 1 minus 1. That's going to give us an issue here. So let's go through and let me actually alleviate this issue really quickly. Give me 1 second. All right, here we go. Now I want to actually make a change here. Yeah, it wasn't going to be that nice if it wasn't. All right, here we go. So let's start then now looking at this, and I'm actually not going to start it at n is equal to 1. I'm actually going to go to n is equal to 2 and then start it from there just to see what happens as we start going through this. So, all right, so we made those changes, those appropriate changes, and what I'm going to do is starting at 2, so in here we're going to get 2 divided by 4 minus 1, so we're going to get 2/3. All right, and then we're going to just keep adding the next term. So if the next term is 3, that's going to be 9 minus 1, and that's going to be 8. So here we go. The next term, it's going to be 4 squared. That's going to be 16 minus 1. That's going to be 15. So that's going to be 2 over 15. And we can just keep going. All right. Now, we can then start saying, okay, well, is there a common ratio? It doesn't look like there's a common ratio, so that's kind of out of the question. Right? We want to identify whether it's convergent or whether it's divergent. All right, so we can then start looking at the limit. Will the limit of this be equal to 0? Well, we don't know that, and that's not going to help us because we don't want to use the converse. We don't want to say, is the limit equal to 0? Then it's going to converge because, again, converse is not true. So we can't test the limit for that to be at our advantage. So we actually have something better. We actually have what is known as, I know I'm taking a break here, we have what's known as partial fraction decomposition. Now, partial fraction decomposition. If you remember, I called this PFDC. So I said, hey, you must use PFDC. And this was a technique that we learned for integration that helped us integrate some of these rational functions and it made them a little bit easier. They made them more manageable to integrate. So we're going to use the same technique. We're going to use the technique of partial fractions in order to figure out what is this fraction going to break down into. Well, in order for me to be able to break it down, I need to first identify that I do have a difference of squares in that denominator. Secondly, analyzing the denominators, I'm going to see that one of my denominators should be just n minus 1 because it's a linear term. One of my other denominators should be n plus 1, and again, because that's a linear term. Each coefficient will have their own coefficient, a and b. So what I'm going to, each numerator will have its independent coefficient. So now I'm going to multiply both sides by the LCD, which means I should get 2 is equal to a times n plus 1 plus b times n minus 1. Now, going through this, all we need to do is combine my like terms, like such. And then we're going to have that a plus b must be multiplied n plus a minus b, and that's going to be equal to 2. So here we have that a plus b must be equal to 0, and we also have that a minus b must be equal to the constant of 2. All right, that's not too bad. So this is a system of equations, and we're going to solve. Yay! So solving this shouldn't be too bad. I can use the addition method. So using the addition method or the elimination method, we're going to get 2a is equal to 2, which means a is equal to 1. Now, if a is equal to 1, then that means b automatically becomes negative 1. So finding these two values, we now have that my a coefficient is just 1, and that's over n minus 1. And then we're going to subtract out my b coefficient. Oops, excuse me, it's not b. Subtract 1, because that's going to be minus 1, over n plus 1. And that's a new value I input here. Minus 1 over n plus 1. So look at that. It's not too bad, right? So we used partial fraction decomposition to break it down. There we are. And it looks pretty good. Now let's start expanding and let's see what happens. All right, so if we start expanding here, so I'm going to have n is equal to 2, so that's going to be here. All right, so that's going to be 1 over 1 minus n is equal to 2. That's going to be 1 over 3. Plus, and again, that was that first term. Second term, all right, the n is equal to 3, so that's going to be 1 over 2 minus 1 over 4. All right, let's go to the next term. N is equal to 4, so this is going to be 3 minus 1 over 5. All right, and we can keep doing this all day long. And again, we're just looking at here, this is n is equal to 2. That was this whole piece. This piece here was n is equal to 3. And then this whole piece was n is equal to 4. And the reason I'm doing this specifically is so that we can then see what's taking place. Well, what do you notice between the 1/3? Well, they're going to cancel. All right, so 1/3 are going to cancel and they're just going to go away. It's not too bad. All right, let's see what else is going to happen. All right, if I were to kept going, this would have been actually, let's see, 3 minus 1, 4 minus 1. So yeah, everything is looking pretty good. All right, so if I wanted to keep going, and I'm going to keep going just to show you one more. This is n is equal to 5, so this is going to be 1/4 minus 1, what is that, 6? Yeah. This here's for n is equal to 5. There we are. So the 1/4 are going to end up canceling. There we are. And that's what we're going to be left with. Now, as it's looking like here, well, we have some values that we're going to be looking for. All right, and so what we see here is that the 1/3 canceled, the 1/4 canceled, the 1/5 are going to cancel next, and then the 1/6 after that, so on and so forth. So if we keep just going off to infinity, it means that the rest of the terms are going to be canceling. So we want to make sure we identify that. And what we have left, well, we have a 1 left over plus 1/2, and then the rest of the terms are the ones that are canceling each other out. So if we did n is equal to 6, then the 5ths would cancel. If we did n is equal to 7, then the 6 would cancel, and then it just keeps on going forever and canceling each other out. Which means this has a sum of 3/2. Now, it's not so apparent up here because, again, we had no value given to us that could be interpreted as a common ratio. This in here is known as a telescoping series. So this is a telescoping series specifically because the terms are canceling each other out the further you go. So the further out you go at each step, the terms are going to keep canceling each other out. All right, that is what we call a telescoping series. So if you're trying to use different tests, different methods to see whether a series is convergent or not, give it a shot. See if it's convergent. See if it's convergent, see if it's divergent, and see if you're able to determine, is it going to be telescoping? If it's going to be telescoping, great. Then you'll be able to figure something out. All right, so let's look at this one here. Oops, my apologies. I forgot to say that this is convergence. So series converges. Not all telescoping series will converge, but the whole process of the telescoping series is so that we can then analyze what isn't taking place. All right, so we're going to use this example for part B. All right, here we go. So we could try to use partial fractions to break this down a little bit more and analyze it. My suggestion would be not to. All right, so my suggestion here is to try the test for divergence. So let's look at that test for divergence then. Well, the test for divergence says that if we can find what the limit is, let's say that the limit as k is approaching infinity for k squared divided by k squared minus 2k plus 5. Let's see if we can find out what this limit is, right? Because that's what the test for divergence says. The test for divergence says you must test the limit of the explicit function that you're analyzing within that series, and if the limit as that function goes towards infinity, then to use the test for divergence, it must either not exist or be not equal to 0. So that's all we have to get, is that this limit must not be equal to 0 or it must not exist. All right, so let's see what's going to happen here. Well, taking that approach, you know what? I'm going to use the approach here of L'Hopital's rule. And again, we can use L'Hopital's rule here specifically because when we take the limit, we get infinity over infinity, which is one of the indeterminate forms that we like to look at. So in here, let's see, that's going to be 2k divided by 2k minus 2. And again, I get infinity over infinity, so I'm going to use L'Hopital's rule again. Which is just 1. So now looking at the test for divergence, the test for divergence says, hey, one of the conditions is that the limit does not exist. Well, we don't have that issue, or sorry, we have that issue that the limit does exist, so that's a problem. Well, the second one is the or statement. So one of these needs to occur. As long as one of them occurs, that's fine. Well, the second one occurred. We got a limit that's not 0. So what does that mean for us? Well, that's going to tell us that the series is divergent. So I'm going to say here, since the limit as, let's say, k goes towards infinity for a sub k is not 0 because it's 1, the series is divergent. And it's as straightforward as that, folks. All right, so this is the whole concept that we look at when we're talking about sequences and series, right? It all stems from these two videos and knowing how to work with them and how to use these different tests. Now, for most of Chapter 11, we're going to be developing different tests to determine whether a sequence or a series is divergent or convergent, all right? So for the next few sections, this is exactly what we're going to be working with. All right, so I hope you all enjoyed this lesson, and I will see you all here for the next one.